Controlling the speed of a DC motor sounds simple, but the naive way of doing it wastes a lot of energy. If you just add a variable resistor in series with the motor, that resistor burns off the extra voltage as heat instead of giving you real control. There's a smarter way to do it, and it uses pulse width modulation.
Here's the complete schematic of the circuit we'll be building. Now let's move on and connect every component one by one so you understand exactly how each part fits into the circuit. We start with the input supply. Power comes in through the input terminal and passes through the switch. From the switch, this positive line branches out and feeds every part of the circuit that needs power.
The first thing we connect off this positive line is a 1K resistor. One end goes to the positive rail, and the other end connects to a junction shared by two 1N4007 diodes and a 100K potentiometer. The two diodes are wired back-to-back around the potentiometer, one for the charging path and one for the discharging path. The wiper of the potentiometer connects onward to the timer IC. This whole network is what will control our motor speed.
From this junction, we run a wire to the discharge pin of the 555 timer. The potentiometer's wiper also connects to the threshold and trigger pins of the IC, which are tied together. Right at this same point, we connect a 0.1 microfarad capacitor down to ground. This capacitor is what charges and discharges through the potentiometer and diodes, and that charge-discharge cycle is the heart of the timing. Next, we wire up the power pins of the 555. The VCC pin connects straight to the positive rail, and the reset pin connects there too, so the timer is never held in reset. The ground pin goes to ground. We also add another 0.1 microfarad capacitor between the control voltage pin and ground. This keeps the internal reference steady. With the timing side wired, we move to the output. The output pin of the 555 is where the switching signal comes out, and from there we run a wire through a 1K resistor before it reaches the gate of the MOSFET. Now for the MOSFET itself, an IRF540N. The source pin connects to ground. The drain pin connects to one terminal of the motor. The other terminal of the motor goes back to the positive rail. Finally, we place a third 1N4007 diode directly across the two motor terminals. This diode protects the MOSFET from the voltage spike the motor generates every time it switches off. With every connection in place, let's understand how this circuit actually works. The 555 timer runs in Astable mode, and it produces a continuous square wave output at its output pin. The duty cycle of this square wave, meaning the proportion of each cycle that the output stays high versus low, is set by the potentiometer working together with the two diodes. Turning the potentiometer changes how long the capacitor charges and how long it discharges, and that directly shifts the duty cycle of the output pulse. This output goes to the gate of the MOSFET, and the MOSFET behaves like a very fast switch, controlling how much current flows through the motor. A wider pulse, or a higher duty cycle, keeps the MOSFET turned on for longer in each cycle. That lets more current pass through the motor, so it spins faster. A narrower pulse, or a lower duty cycle, keeps the MOSFET on for less time, so less current reaches the motor and it spins slower. The diode placed across the motor protects the MOSFET from the back electromotive force generated when the motor's magnetic field collapses every time it switches off. Without it, that voltage spike could damage the MOSFET. And that's how a simple 555 timer and a MOSFET can give you smooth, efficient control over your DC motor speed without wasting a single bit of energy as heat. If you found this explanation useful, do like this video and subscribe for more circuit breakdowns like this one. Drop your questions in the comments, and I'll see you in the next video.